And now in this lecture you find out the area of a semicircle. In the drawing we have a semicircle that is inscribed by this quarter circle AOB. You know that arc AQ equals to arc QB. This is line segment OS, this equals to 3 units in Islam. This is angle AOB. This is a right angle because AOB is a quarter circle. Again, our task is to find out the area of this semicircle. So first of all, we define the center of this semicircle. This point is point C. We define the radius of this circle, of this semicircle. It's R. Point S is the point of tendency of tangent OB with this semicircle. We join point C and S together by a straight line. Point C is the center of the semicircle. Point S is the point on the semicircle itself. Therefore, CS is the radius of this semicircle that is equal to R according to our definition. The radius CS equals to R. The radius CS is drawn to point S, that is the point of tendency of tangent OB with this semicircle. And now you have this that is drawn to the point of tendency. And now you have this that is drawn to the point of tendency, then tangent OS will be perpendicular to the radius ASO. According to rule 1. If OS, then tangent OB will be perpendicular to the radius SC. If OB is perpendicular to SC, it means that this angle equals to 90 degrees. And this angle also equals to 90 degrees according to rule 1. So, the next step, we'll do a construction. First of all, we define this point that is actually the touching point between this semicircle and side AO of the quarter circle. This point is point P. In the next step, we'll do a construction. That is to say, from point Q, that is actually the touching point of this semicircle with this quarter circle. From point Q, we will go perpendicular on OB. Again, from point Q, we will go perpendicular on OB. So actually, this angle equals to 90 degrees, and this angle also equals to 90 degrees, according to our construction. We define the touching point of the perpendicular from point Q and OB. This point is point M. Here we can implement rule 22. We can quickly on rule 22. According to rule 22, if the sum of two one-sided intervals is equal to 180 degrees, then they are located between parallel lines. So in the drawing, you have line A that is parallel to line B. The red line C cuts those two parallel lines. Or you can say that we have line A that is, we don't know that line A is parallel to line B, and we have line C that cuts those two lines that we don't know if they are parallel to each other or not. But we do know that the sum of those two interrogants is equal to 180 degrees. That is to say, alpha plus beta equals to 180 degrees. And because of the fact that the sum of those two interrogants is equal to 180 degrees, from the fact that the sum of those two interrogants is equal to 180 degrees, we observe that they are located between parallel lines. That is to say, line A is parallel to line B. So if the sum of those two interrogants is equal to 180 degrees, then line A is parallel to line B. Those two angles, alpha and beta, are defined as complementary angles. To complete the sum of them is 180 degrees. If the sum of them is 180 degrees, then line A is parallel to line B. So we can actually implement rule 22 in our drawing. In our drawing, we have those angles now defined as complementary angles, the interangles. The sum of those two right angles is of course 180 degrees. And because of the fact that the sum of those two complementary angles is equal to 180 degrees, they must be located between parallel lines. That is to say, PO is parallel to CS. Likewise, those two interangles, the sum of those two interangles is 180 degrees. And because of the fact that the sum of those two interangles is equal to 180 degrees, they are located between parallel lines. That is to say, CS is also parallel to OM. Likewise, those two complementary angles, they are one-sided interangles, they are located, the sum of those two interangles is 180 degrees, and therefore they must be located between parallel lines. That is to say, PO is parallel to QM. So in total, we found out that PO is parallel to CS is parallel to QM, according to rule 22. So write it down. We found out that PO is parallel to CS is parallel to QM. So the three lines PO and CS and QM are parallel to each other. And again, those three lines, they are parallel to each other, and therefore we can implement here Tell's theorem. And again, because of the fact that we have here three parallel lines, we can implement Tell's theorem. Actually, Tell's theorem is about if you have three parallel lines or more than three parallel lines, and you have a relationship between the lines that connect the parallel lines. Again, the lines that connect the three parallel lines are PQ and OM. So whenever you have three parallel lines, PO is parallel to CS to QM, you can implement Tell's theorem, because Tell's theorem gives us the relationship between the straight lines that connect the three parallel lines. The straight lines that connect the three parallel lines are PQ and OM. We have a special relationship between PQ and OM. Actually, according to Tell's theorem, PC over CQ equals to OS over SM. Again, PC over CQ equals to OS over CM. And again, in the drawing, we have PO is parallel to CS is parallel to QT. Those three lines are parallel to each other. PO is parallel to CS is parallel to QT. And the two lines that connect the three parallel lines are PQ and OT. This theorem gives us the relationship between the two lines that connect the three parallel lines, between PQ and OT. According to this theorem, PC over CQ equals to OS over ST. Again, PC over CQ equals to OS over ST. Okay, so whenever you have three or more parallel lines, you can implement Tell's theorem. In this case, we have three parallel lines, and therefore you can implement this Tell's theorem in our drawing. Those three lines are parallel to each other. And again, according to Tell's theorem, we get that PC over CQ PC over CQ equals to OS over SM. Is again because of the fact that we have here three parallel lines, you can implement this theorem that talks about the relationship between the two lines that connect the three parallel lines, between line PQ and line OM. According to this theorem, the following equation is true, that PC over CQ equals to OS over SM. This equation is the implementation of this theorem in our drawing. PC is of course the radius of the circle that is equals to R. CQ is also the radius of the circle that is equals to R. According to our definition. So PC is R, over CQ is also R, and it's equal to OS, that is 3 according to what is given us the question, over SM. SM is the missing side, so we leave it as it is. In total, according to this theorem, found out actually that R over R equals to 3 over SM. R over R is 1. So 1 equals to 3 over SM. Here we will multiply this equation by SM, and finally get that SM equals to 3 units in its length. SM equals to 3. This is side SM that is equals to 3 units in its length. In the next step, we join points O and Q together by straight line. And again, we join points O and Q together by straight line. It is given us in the question that RKQ is equal to RQB in a quarter circle AOB. Again, according to what is given in the question, RKQ is equal to RQB in its size. And therefore, we can implement rule 23. Repeat quickly rule 23. According to rule 23, side angles that subtend on equal arcs are equal to each other. You know, drawing a circle. This is side angle AOB that subtend on arc AB. Likewise, this is side angle COD that subtend on chord CD. And according to this rule 23, if arc AB is equal to arc CD in its size, that is to say, those two center angles subtend on equal arcs that must be equal to each other in their sizes. That is to say, if arc AB is equal to arc CD, then center angle AOB equals to center angle COD. If the size of center angle AOB is alpha and the size of center angle COD is beta, then alpha equals to beta. So, according to rule 23, if two center angles subtend on equal arcs, they must be equal to each other in their sizes. In this case, if arc AB is equal to arc CD, then alpha equals to beta. So we can definitely implement rule 23 in our drawing. One could in our drawing. It is given us the question that RKQ is equal to RQB in its size. This is center angle AOQ, that's subtend on RKQ. This is center angle BOQ, that's subtend on RPQ. And according to what is given as the question, the size of RKQ is equal to the size of RQB. And therefore, whenever you have two center angles that subtend on equal arcs, like here, they must be equal to each other in their sizes. That's to say, the size of center angle EOQ must be equal to the size of this center angle QOB. So if the size of center angle AOQ is theta, then the size of center angle QOB must be equal to theta because they are equal to each other according to rule 23. AOB is a right angle because AOB is a quarter circle, therefore AOB is a right angle because this is the definition of quarter circle. This is always a right angle in any quarter circle. So theta plus theta equals to 90 degrees. Theta plus theta is 2 theta is equal to 90 degrees. We divide this equation by 2, we get that theta equals to 45 degrees in its side. So this is angle AOQ is equal to theta, that is 45 degrees. This is angle QOB, that is also equal to theta, and theta equals to 45 degrees in its size. In the next step, we'll focus on the right angle QOM. This is right angle QOM. In the right angle QOM, tangent 45 degrees. Is equal to QM over MO. Repeat again. The right angle QOM. Minus 45 degrees equals to QM over MO. Tangent 45 degrees is 1. So 1 equals to QM. QM is the missing side, so leave it as it is. Over MO. MO equals in total to 3 plus 3, that is 6. 3 plus 3 is 6. So in total, we should follow that one equals to QM over 6. Here we multiply this equation by 6. And finally, we get that QM equals to 6 units in its length. This is the side QM. Is equals to 6 units in its length. in the next step, we will do another construction. That is to say, from point C, that is the center of the semicircle, we will draw perpendicular on QM. Again, from point C, we will draw perpendicular on QM. So if this angle equals to 90 degrees, this angle also equals to 90 degrees according to our construction. When we find the touching point of the perpendicular from point C and QM, this point is point N. When doing this construction, we have quadrilateral CNMS. Inside this quadrilateral CNMS, we have 1, 2, 3 right angles. The sum of 3 right angles is 270 degrees, so 270 degrees plus the size of this 450 degrees. In total, it must be equal to 360 degrees. According to the rule, that the sum of the angles in any quadrilateral is equal to 360 degrees. And therefore, this 450 degrees must be equal to 90 degrees in its size. So in quadrilateral and CSM, we have 4 right angles, and according to all 5 in the quadrilateral that has 4 right angles must be this left angle not a square. So we get to this quadrilateral and CSM is left angle because it has 4 right angles. But we also know that the opposite sides of left angle are equal to each other. So left angle CNMS, side CN must be equal to the opposite side SM, but SM is 3, therefore CN must be also equal to 3 units in its length. Likewise, according to the sum rule, in the sum left angle CNMS, side CS, left angle CNMS, side CS must be equal to the opposite side NM. But CS is the radius of the semicircle that is out, therefore the opposite side QM must be equal to R units in its length. We already found out that QM in total is 6, therefore NQ or QN equals to QM that is 6 minus NM that is R. So in total NQ equals to 6 minus R units in its length. So again, I should find out QN equals to QM equals QM equals to QN equals to QM minus NM. The small answer at QN equals to QM minus NM. So QN equals to QM that is 6 minus QM that is R. So in total, we should find out that the small answer at QN equals to 6 minus R units in its length. So in the next step, I'll copy right triangle QCN, this small right triangle QCN. In the equation, we implement the Pythagoras theorem on this small right triangle QCN. According to the Pythagoras theorem, in any right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. carefully. This is right angle QCN, the point from the original line. This right angle QCN according to the Pythagoras theorem. QC squared, that is the square of the hypotenuse, equals to QN squared plus CN squared. So I write it down. QC squared, that is the square of the hypotenuse, is equal to Qn squared plus Cn squared. The hypotenuse QC is the radius of the semicircle that is R, so QC squared is R squared, and it is equals to Qn squared. Qn is 6 minus R, therefore Qn squared is 6 minus R squared plus Cn squared. Cn is 3, therefore Cn squared is 3 squared, that is 9. So to that, we should found out that R squared equals to 6 minus R squared plus 9. Here we'll open the brackets on this side of the equation of this expression, and we get that R squared equals to 6 minus R squared. 6 minus R squared equals to 6 squared, that is 36, plus R squared, minus 2 times 6 times R, that is minus 12R, plus 9. You have R squared both sides of this equation, so R squared gets cancelled. So in this side of the equation we have nothing, that is to say 0, and on the other side of the equation we have 36 plus 9, that is 45, minus 2R equals to 0. Here we add 2R to this, 12R to this equation. Again, the 12R equals to 45. Here we divide this equation by 12, and when we get that the radius R of the semicircle, that's it's area that we are looking for this question. The radius R equals to 45 over 12. Here we divide both the numerator and the denominator of this number by 3 and get that 45 over 3 is 15, and 12 over 3 is 4. So in total we should find out that the radius of the semicircle, the radius R equals to 15 over 4 units in its length. Our task is to find out the area of this semicircle. Not the area of any semicircle is equal to the area of the circle, that is pi r squared. R is the radius of the circle. Therefore, the area of the semicircle is equal to pi r squared over 2. So in total, the area of the semicircle equals to pi over 2 times r squared. R is 15 over 4, therefore r squared is 15 over 4 squared. So in total, the area of the semicircle equals to pi over 2 times 15 over 4 squared. So it is pi over 2. And we have 15 over 4 squared is 15 squared, that is 225. Over 4 squared, it is 16. So if we found out that the area of the semicircle equals to 225 pi over 2 times 16. So it is 225 pi over 2 times 16, that is 32. So in total, if we found out that the area that we are looking for in this question, that is the area of this semicircle, is equal to 225 pi over 32 square units in size. In terms of numbers, it is equal to 22.09 square units in size. So again, the area of this semicircle, that is the area that we are looking for in this question, it is equal to either 225 pi over 32 square units in size, or in terms of numbers, it is equal to 22.09 square units in size. So finish with the answer to the question. So in the next step, I'll solve the lecture. question, our task is to find out the area of this semicircle that is inscribed by this quarter circle ABQ. So in the drawing we have a semicircle that is inscribed by this quarter circle. RKQ equals to RQB in its size. OS equals to 4 units in itself. This is again AOB, this is right angle. Again, our task is to find out the area of this semicircle. So first of all, we define the center of this semicircle. This point is point C, and point S is the point of tendency of tangent OM with this semicircle. We join point C and S1 over a straight line. Point C is the center of the semicircle. Point S is the point on the semicircle. Therefore, CS is the radius of the circle that we define as R. The radius CS is equal to 1. The radius CS is 1 to point S, that is the point of tendency of tangent OM with this semicircle. And whenever your radius is 1 to the point of tendency, then tangent OM will be perpendicular to the radius SC. OM is perpendicular to SC, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees according to rule 1. In the next step we did the construction, that is to say from point Q, we draw perpendicular on OB. Again from point Q, we draw perpendicular on OB. So this angle equals to 90 degrees, and this angle also equals to 90 degrees according to the construction. We define the touching point of the perpendicular from point Q and OB. This point is point M. So here I can implement rule 22. Rule 22. According to rule 22, if the sum of two one-sided interangles is equal to 180 degrees, then they are located between parallel lines. In the drawing, we have line A and line B. The line C cuts those two lines, and we have those two angles alpha and beta that are defined as one-sided interangles. According to this rule 22, if the sum of those two one-sided interangles is equal to 180 degrees, then they are located between parallel lines. That is to say, line A is parallel to line B. Again, according to this rule 22, if the sum of those two one-sided interangles is equal to 180 degrees each side, then line A is parallel to line B. So we can implement rule 22 in our drawing, when we put the sum of those two one-sided interangles is 180 degrees, and therefore they are located between parallel lines. That is to say, PO is parallel to CS. Likewise, the sum of those two one-sided interangles is equal to 180 degrees, because 90 degrees plus 90 degrees is 180 degrees, and therefore they must be located between parallel lines. That is to say, CS is parallel to QM. And finally, the sum of those two one-sided interangles is 180 degrees, therefore they must be located between parallel lines. That is to say, PO is parallel to QM. So if you found out that all the three lines are parallel to each other. That is to say, PO is parallel to CS, is parallel to QM. And whenever you have three or more parallel lines, you can implement Tell's theorem. According to Tell's theorem, we have a special relationship between the lines that connect the three parallel lines. PM connects those three parallel lines, and line OM also connects these three parallel lines. We have a relationship, special relationship between those two lines, PQ and OM, that connects the three parallel lines. The relationship is as follows: PCO over CQ equals to OS over SM. Again, PC over CQ equals to OS over SM. Repeat again on test theorem. According to test theorem, whenever you have 3 or more parallel lines, and we have other lines that are not parallel to the other lines that are not parallel, here PQ is not parallel to OT. The other line connects the 3 parallel lines, PQ connects the 3 parallel lines, and OT also connects the 3 parallel lines. Then we have a special relationship between those two lines PQ and OT. The relationship is as follows: PC over CQ equals to OS over ST. Again, PC over CQ equals to OS over ST. So we can actually implement all the test theorem in our drawing, because we have here 1, 2, 3 parallel lines. PQ connects the 3 parallel lines. OM also connects the 3 parallel lines. We have a special relationship between PQ and OM that connects the 3 parallel lines together. The special relationship, according to the theorem, is as follows: PC over CQ equals to OS over SM. Again, PC over CQ equals to OS over SM. And again, according to the theorem, PC over CQ equals to OS over SM. PC is the radius of the circle that is R, PQ is also the radius of the semicircle that is R. Is given as the equation that OS is 3, SM is the missing side. Take again, PC is R, CQ is also R, OS is 3, SM is the missing side. So in total, if you follow that R over R equals to 3 over SM. R over R is 1, so 1 equals to 3 over SM. Here we multiply this equation by SM, and we found out that SM equals to 3 in this length. This is line segment SM, this equals to 3 in its length. In the next step, we join points O and Q together by a straight line. By joining points O and Q together, there are triangle QOM, and we have, it is given as a equation that RKQ is equal to RQB in its size. Those two arcs are equal to each other in their sizes. This is a triangle AOQ that subtends on RKQ. Again, this is a triangle AOQ that subtends on RKQ. Likewise, this is a triangle MOQ that subtends on RQB. And because of the fact that those two triangles subtend on equal arcs, because AQ is equal to QB, they are equal to each other in their sizes. And again, rule 23, according to rule 23, triangles that subtend on equal arcs are equal to each other in their sizes. So in the drawing, second, this is triangle OB that subtend on RKB. This is triangle COQ that subtend on arc CD. So if arc AB is equal to arc CD in its size, then those two triangles must be equal to each other in their sizes. That is to say, alpha equals to beta. Triangle AOQ subtend on RKQ. Triangle QOB subtend on RQB. And because of the fact that those two arcs are equal to each other, those two triangles must be equal to each other in their sizes. So if the size of this triangle is theta, then the size of this triangle must be also equal to theta, because they are equal to each other in their sizes. Theta plus theta is 90 degrees, because this is a right angle. Theta plus theta is 90 degrees. Theta plus theta is 2 theta, that is 90 degrees. We divide this equation by 2, and we found out that theta equals to 90 degrees over 2, that is 45 degrees. So this angle equals to 45 degrees, and this angle also equals to 45 degrees in its size. So in triangle, the right angle QOM, triangle is 45 degrees, equals to QM over MO. Again, the right angle QOM, times 45 degrees equals to QM over MO. Again, the right angle QOM, times 45 degrees equals to QM over MO. Times 45 degrees is 1. MQ is the missing side. OM equals to 6. OM in total equals to 3 plus 3, that is 6. And here, OM equals to 6. So in total, if you know that MQ over 6 equals to 1, here we multiply this equation by 6, and for that QM equals to 6 units in its length. This is 97 QM, that equals to 6 units in its length. In the next step, we did another construction, that is to say, from point C, that is the center of the circle, we do perpendicular on QM. Again, from point C, we do perpendicular on QM. So this angle equals to 90 degrees, and this angle equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point C and QM. This point is point N. When doing this construction, we created quadrilateral CNMS. In quadrilateral CNMS, we have 1, 2 vertices. The sum of vertices is 270 degrees. So 470 degrees plus the size of this 4 pieces again. Total must be equal to 360 degrees according to the rule that says that the sum of the angles in a quadrilateral is equal to 360 degrees. And therefore, this 4 pieces again must be equal to 90 degrees in its size. Therefore, quadrilateral SNMS is a rectangle because it has 4 rectangles. But we know that the opposite sides of a rectangle are equal to each other. So in rectangle CNMS, side CN must be equal to the opposite side MS. But MS is 3, therefore the opposite side CN must be also equal to 4 units in its length. Likewise, according to the symbol, with the sum rectangle CNMS, side CS must be equal to the opposite side NM. But CS is R, it is the radius of the circle, but so NM must be also equal to R units in its length. What is the length of QN? The small 97 QN equals to QM once NM. Again, QN equals to QM once NM. QN equals to QM once NM. So QN equals to QM, that is 6, once NM, that is also. So the small 97 QN equals to 6 once R units in its length. In the next step, I copied the small rectangle QCN in the new page. We implemented the quadratic theorem on this small rectangle QCN. According to the quadratic theorem, in any rectangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. So this is the rectangle QCN. This is the point from the original drawing. In this rectangle QCN, CQ squared, that is the square of the hypotenuse, equals to QN squared plus CN squared. CQ is out, so again, QC squared equals to QN squared plus CN squared. QC is out, therefore QC squared is R squared plus QN squared. QN is 6 times 1, therefore QN squared is 6 times 1 squared plus CN squared. CN is 3, therefore CN squared is 3 squared, that is 9. So total, if you found out that R squared equals to 6 times R squared plus 9. Here open the brackets of this expression, and find out that R squared equals to 6 times R squared. 6 times R squared equals to 6 squared, that is 36, plus R squared, minus 2 times 6 times R, that is minus 12R, plus 9. We have R squared on both sides of the equation, so R squared will be cancelled, and left only in this side of the equation we left with nothing, that is to say 0, while in the other side of the equation we have 36 plus 9, that is 45, minus 2R. 45 minus 2R equals to 0. Here we added 45 minus 12R equals to 0. We added 12R to this equation, and we found out that 12R equals to 45. Here we divided this equation by 12, and find out that the other side, the same circle, equals to 45 over 12. We divided both the numerator of this number by 3. 45 over 3 is 15, 12 over 3 is 4. So in total, if we find out that the other side of the circle equals to 15 over 4 units in its length. Our test is to find out the area of this semicircle. Should we know that the area of any circle, and the area of any semicircle equals to the area of the circle, that is pi r squared. The area of the semicircle is equal to pi r squared over 2. So it is pi over 2 times r squared. R is for 15 over 4, therefore r squared is 15 over 4 squared. So in total, we found out that the area of the semicircle equals to pi times 15 squared over 2 times 4 squared. So it is pi over 2 times 15 over 4 squared equals to 15 squared, is 225, over 4 squared, it is 16. So in total, the semicircle equals to 225 pi over 2 times 16. 2 times 16 is 32, so in total we found out that the area of this semicircle equals to 225 pi over 32. 225 pi over 32 is equal to 22.09 square root in its size. Okay, again, I should find out that there of this semicircle that is there that we are looking for in this question. It is equal to either 225 pi over 32 square root in its size, or in terms of numbers, there of this semicircle equals to 22.09 square root in its size. Okay, thank you very much.